Okay, we'll talk about the linear algebra, which is required for machine learning. Okay, let's start with an example, and then we'll build the intuitions behind what is required. Let's say I have to build a okay, robotic hand basically, and I wanted to place an object from A to B. Okay, and let's say I have an apple here. This is my robotic hand. I wanted to take this apple from this position, and I wanted to place it here. Okay, and then the robot hand has to take it from here and place it back to the original source that it taken. So you see that there is a movement of my hand. Okay, and it is taking this actually, and it can take multiple paths. Okay, you can go like this, or I can probably stretch and keep it like this. Okay, or it can rotate and bring it back here. Okay, and these are some of the actions. Okay, so what linear algebra essentially means is that it can either rotate or scale. Okay, and the things cannot bend. Okay, that's what is meant by linear algebra. So if I wanted to take this, if my hand is a robotic hand, and if I wanted to take this apple from this point A and place it to point B, okay, and then bring it back here. Actually, basically, what I'm doing is I am kind of rotating, or I can rotate like this and scale like this. Okay, there are multiple ways I can do that actually. So linear algebra deals with this rotation of scaling of an object. Okay, let's say I have an initial position. Okay, in order to understand the initial position, I need to talk about vectors actually. So let's say that we have an xy axis. Okay, and this is x and this is y, and my apple is here. Okay, my apple is here. Sorry, this is what let's assume that this is an apple. Okay. My apple is here, and I wanted to take the apple from here and place it here. So what it means is that I'm taking it this location A and I'm pointing at location. There is a rotation. Suppose I wanted to kind of take this apple here and I just place my apple here. Okay, apple here. Okay, which means that I'm scaling my this axis to this location. So either I can rotate it or scale it. That is what linear algebra is all about in a nutshell. Okay, I can rotate, scale, okay, or I can shear. I can come from I can take the apple from there and place it here. Okay, so there are multiple ways I can do it. So a vector is just a representation of a point in a plane. Okay, let's say this is an x-axis. Let's say this is 1, 2, 3. Okay, 1, 2, 3, and this is y-axis like 1, 2, 3. And what at this point the apple is positioned at the point 3 units on the x-axis and 1 unit on the y-axis, so it's 3, 1. So anything which has a direction, which is called as a vector. So for example, if I just say 3, if you wanted to if you wanted to travel from a point A to B, okay, you cannot just tell that, okay, if I want to travel from say Chennai to Bangalore, okay, I need to tell which direction I need to travel. Okay, otherwise I cannot just say go. Okay, they might go in opposite direction. From instead of going to Chennai, from Bangalore, they might go southwards and go to a different city. If you just start a car. Okay, so direction plays an important role. Whether you need to go east, west, north, or south to attain a destination. Similarly, a vector represents both magnitude and direction. Magnitude is 3 units from x-axis, 1 unit from y-axis. Okay, and this is what the vector is. And what this vector, if I wanted to play, if I assume that I have a robo hand, okay, I wanted to place it there. I scale this vector from this point A to point B, okay, and if I wanted to put it in this position B, I kind of rotate it. So how does this happen? How does this vector kind of rotate or scale? Okay, it is done through a matrix actually. Okay, so what it really means is that vector is represented by x, y, and matrix is represented by a series of kind of x and y pairs. Okay, which kind of acts on this vector and it either rotates or scales. Okay, that is what matrix is actually. Okay, so let's take an example again. I'll repeat with another example of what a scalar is. Okay, let's say I have This is a scalar. It does not have any direction actually. If I have 1 comma 2, which means that I go, I represent it as like x-axis is 1 and y-axis 2. This is vector. This is a scalar and this is a vector. Actually, scalar you don't represent in a bracket in brackets. You just represent it like this. Vectors you start representing in brackets. Okay. And then if it is a matrix, you represent like 1, 2, 3, and 4. If you have multiple vectors, you can club together into a matrix. Actually, matrix is again a collection of vectors. If you have a collection of multiple matrices, then we call it as tensors. Okay, you have matrix 1, matrix 2, matrix 3, and matrix 4. So this is called tensor. So this is scalar, this is vector, this is matrix, this is tensor. Okay, so TensorFlow means that it deals with high dimensional matrices. That is what you mean by tensor. That's why it is named TensorFlow. Okay, and what matrix does to a vector is it kind of either scales or rotates, or either it can be scaling can be outwards or it can be inwards, and it can shade. Okay, so similarly, I mean like if you take an example like this, okay, I'll just show an example. I'm not sure if you're able to see it. Let me come closer. Let me just make it as a cylinder. And if you see two arrows, right? Two arrows. Consider there are two different vectors, okay? And if you see, this is called rotation. Look at this vector, which is like pointed out here, okay? It moves here, okay? This is scaling. So this is rotation. And if you see this vector, which is like kind of not rotating, but just shrinking or expanding, this is called scaling. So when you multiply the vector by a matrix, this is what it does to a vector. Okay, and if you also noticed that there was okay, I'll tell you later. So you understand what is a vector? Vector is just a representation of a point in a space. Okay, it can be in x y direction. If it can be multiple higher dimension as well. Okay, if we have 3 dimension, it is like 1, 2, 3 x y z. If you have 4 dimension, it is like x y z a. Okay, how many dimensions you want, you can have vector. But just for representation, I have given it in 2 dimensions to make it easy. Now. You know matrix when multiplied by vector, it either scales or rotates. That's what it does. Okay, and why do we need that? Okay, we need to transform a point from A to B for some benefits. Actually, you don't do it just for fun. If you probably do it, and then it makes our computations easier. It makes our understanding of the data easier. It makes our life easier. That's why you have transformations. For example, if you wanted to have a log transformation, okay, when you take log of two large numbers, it becomes addition. Okay, so addition is kind of easy for us to do than a large multiplication. Right? That's why we transform, to make things easier for us to understand. In case of Fourier transform, what you do is you take a time series data and then convert it into frequency domain, so that you're able to make use of that data. Okay, when all transformations are done to make our calculations and life easier to compute. Okay, that's why. So even the matrix vector multiplication is called as linear transformation. It is used to, make our life easier in computations. Why we do it? We'll see some examples, but understand what the difference between a scalar vector matrix and is actually. Now there is one more concept called determinant. Okay, in matrices, the amount by which the area changes. Actually, for example, you have a vector like this. Okay, let's say 1, 2. Okay, and this is the original position actually. And if you try to increase it, if you try to transform it to this position, okay, the area of the parallelogram, you can call it as like, okay, you can draw. I'll give an example actually. I'll give an example of a determinant. let's say you have a vector of length I 0, 1, and it is like 1, 0. This is the original shape of the vector, okay? And this is the position and position of I hat and j hat. Okay. So what I hat and j hat is called as the basis vectors. What it really means is that before you do any transformation, you assume that there are two vectors I and j which are pointing one unit away from 0 here and one unit away from j here, because this will form the basis. Because if you read, in case of an example of a robotic hand, okay, only if you have a kind of perpendicular axis like this, you can assume that, okay, you take an apple from this position to place it this position. Suppose your axis is like this, okay, which means that the base is rotated. Actually, this is also 90 degree, this is also 90 degree, but this is rotated this way, okay, which means that the basis of the basis has changed from this to this. So now if you try to try to rotate it the same degree as you did it here, for this you might end up in a different location. So we need to know what is the base from which we are starting with. So that is called as basis vectors, and I hat and j hat are used to kind of represent it. So let's say that you have these two vectors, okay, and you multiply by a matrix M, okay, and this, let's say this transforms this I hat to this location, okay, and this so j hat this location and I hat moves to this location, okay, and what happens to this there's a change in area of this original square, okay, and this change in area of this particular square to this parallelogram, okay, look at the size of, let's say this area is A and this is probably like, let's say 3A, okay. This change in area of this vectors caused by this matrix multiplication is known as determinant actually. So determinant tells you whether this has increased in area or decreased in area, or for example if I hat and j hat kind of squishes, like the rotation happens and that, okay, this falls in the same line, okay, which means that I hat and j hat falls in the same line as you rotate and place it here, which means the area from A becomes let's say from this is original A, and it becomes a straight line here, so the area becomes 0 A, which means the determinant of this matrix is 0 actually, okay, because it has rotated in such a way that the area has not either increased or decreased, but it has made it to 0 actually. So that is called zero determinant. So just keep in mind, a matrix transforms a vector either by a rotation or shear. It can expand or contract. The shear means it is like scale is expansion or contraction, okay, scale or shear, or it can rotate, okay, any degrees. And determinant helps you to find out what is the ratio by which it has changed, okay. For example, this determinant has increased, which means that it has caused a massive change in the movement of this particular point, okay, and it has moved here. So it is the change in area is what is called as determinant. So these are all key elements of linear algebra, okay, matrices, determinants, and then scalars and vectors, okay, and this is what you need to know. And I will come back to this position, okay, to this example, and if you see here, there are two arrows, okay. Let's say this is one arrow, this is one arrow. This is we call two vectors actually. So when I try to rotate this, okay, I'm placing this, I assume that my hand is a matrix and I am applying this to the vectors, these two vectors, okay, and what happens is it rotates and it changes the shape of these two vectors actually. So this vector, if you look at it, it completely changes its position from A to B through a rotation. Actually, it rotates. And if you look at this vector, okay, and it does not change its position actually. It either expands or it kind of shrinks. So either it is scaling or it is shrinking. So these vectors are special vectors, which is called as eigenvectors. The value and the ratio by which expands or contracts is called eigenvalue. So now why is this important is when you do a linear transformation, certain
it does change a lot of existing vectors, right? You're applying a matrix to this vectors, and it changes its changes this. I mean the positions, and transform it and disforms it. So now certain vectors like this, which is called as eigenvectors, do not change its position, but I mean, it's in a position. It does change its position, but it is scaling or shrinking. So these are called eigenvectors. These vectors are very important because if you are able to find like 3-4 vectors out of all in the entire matrix, you will be able to reconstruct the entire entire matrix back. Okay, and it will help you to find out the variation. I mean, like, in other words, these vectors have gone to the least transformation, despite having a matrix do something on those vectors. Okay, when you have least transformation, which means that you can retain the original information back. Okay, that's easy. That's the idea. And another idea is when you try to rotate a matrix, like an example of a robo. You take a 3D object actually, okay, and if you're able to find an vector which, when transformed, let's say A to B, let's take an example here. I'll just take an example. Okay, this is an object. Okay, you kind of move from this location to this location, and one vector hasn't changed its axis. So what it really means is that, let's say this vector, if you're able to find one vector which hasn't changed its axis, or I would say this hasn't formed at change its position in terms of xy axes, okay, much, and you are able to find the axis of the matrix. Okay, so which means that you'll be able to rotate everything, but you will still be able to find and hold a vector which is kind of forms the axis of it. Okay, that's the beauty of having an eigenvector. Okay, an eigenvalue is the ratio by which it kind of changes. Okay.